So Boolean algebra and digital logic. All right. All right, they start out with this introduction. It says, in the latter part of the 19th century, George Boole incensed philosophers and mathematicians alike when he suggested that logical thought could be represented through mathematical equations. How dare anyone suggest that human thought could be encapsulated and manipulated like an algebraic formula? And who did George Boole? Someone did George Boole this semester, right? Was it Carndeep? Or no? Who was it? Oh, it was a Todd. So when did George Boole live, Todd?
1800s.
Yeah, in the 1800s. So back in the 1800s, people weren't as open-minded. There wasn't a lot of communication, so people weren't as well-read as they are today. Okay? And so, you know, computers were not even an inkling inside of their brains. They had no idea what computers could be. Okay? Even in this century, they had no idea what computers could be. And so for him to suggest that was a really radical thought. Okay? But he did see the future, and he saw that, yes, we can take all of our logical thoughts and break them down into Boolean algebraic formulas. Okay? So computers as we know them today are implementation of Boole's laws of thought. John Atanasoff and Claude Shannon were among the first to see this connection. So they're the ones who discovered Boole's work and then brought it to the forefront and figured out that he was on the right path for implementing this kind of thing. So in the middle of the 20th century, computers were commonly known as our thinking machines and electronic brains. And of course, many people were fearful of them. Okay, even today, when we talk about the future of artificial intelligence, we have a lot of movies where artificial intelligent robots are taking over the world. And so we still have this fear of computers. Okay? It is good to keep this fear of computers, I think. And maybe that's the human in me saying that, but we do need to always make sure we're doing ethical things with our computers. So nowadays, we rarely ponder the relationship between our electronic digital computers and human logic, and we have accepted them as part of our lives. Okay. In this chapter, we're going to learn how simple the actual hardware is inside of our machine, the actual implementation of this logic. Okay, so Boolean algebra is probably the easiest algebra you can ever use because it only uses ones and zeros, or true or false, high and low. Okay. So Boolean algebra is this mathematical system for the manipulation of variables that can have only two values. And Boolean expressions are created by performing operations on these Boolean variables. And these are our three logical operations: the AND operation, the OR operation, and the NOT operation. And we see those operations in our software, right? We're all programmers. We've all programmed before. And those are our three logical operators. Okay. And that's kind of the basis for all Boolean algebra, is the AND, OR, and NOT operations. And that is actually the basis of all computers, is an AND gate, an OR gate, and a NOT gate. And so this week, sorry, excuse me. This week we're going to go over Boolean algebra, and then we're going to start getting into digital circuits. And we actually have integrated circuit chips, and this week we are doing an Arduino lab, but next week we can start getting into our electronic circuits lab. Okay, and we'll start building these things with the AND gates, the OR gates, and the NOT gates, and figure out how we implement this logic in hardware. Okay. All right, so in review of what an AND operation is, we should all know this. So a Boolean operator can be completely described using a truth table. And you might have had me for first level programming, and I probably told you that these truth tables are the basis of all computing. And going into this Boolean algebra and digital circuits, you'll see why. Okay, these truth tables are the basis of all computing. So here's our truth table for our AND operation. Okay, so this is our first input X and our second input Y. And then sometimes in Boolean algebra, we write x and y as the multiplication of x and y. Okay, so x and y, okay, is only true when they're both true. And x or y is true when only one of them is true. Now the OR operation is usually considered the addition operation. And the AND operation is usually considered the multiplication operation. And you can see that if you say 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 2, but inside of our circuits, we use that overflow and we add it back in, or the carryover, and we add the carry back in. Okay. And then for our OR operation, you can see that it is addition. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1, and 1 plus 0 is 1, and 1 plus 1 is 2, but we take the carryover and add it back in. Okay. Where did we see this in our Arduino labs? Do you remember that lab 1 I gave you? So if we look at our lab 1, remember how I had you put the buttons in series and then the buttons in parallel? Do you remember when we put the buttons in series? What output did you get right here? Do you guys remember? So here's a truth table. We are using off and on, but this is a truth table. It's all combinations of our buttons. Do you remember when we had it in series? So the buttons in series. What was our output? They're all off except for the last one was on. So which logical operation did our buttons in series represent? The AND operation, the multiplication operation. So note that if we have, two buttons in series, or two latches, or whatever you want, switches in series, that's our multiplication operation. That's our AND operation. They are the same. Okay, that's how we've implemented it in hardware. How about this one? When we had them in parallel, when we had the buttons in parallel, what did our output look like? You guys remember? Yeah, it was off, on. And that was our OR operation. Okay, so our OR operation is having switches in parallel. Okay, so you can kind of start to relate these truth tables to the actual hardware. Okay, so when we implement the AND, it's like having two switches in series. And when we implement the OR operation, it's having two switches or buttons in parallel. Okay? All right. So start to make this connection. Okay, the truth table for the Boolean NOT operator is shown at the right. And remember, the NOT operator was pretty easy. And the NOT operation is most often designated by a prime mark. So when we say NOT, we put that little prime mark right there, a little apostrophe thing. Sometimes it's indicated by a bar over that input. So they'll put a bar over it. That means not X. Or sometimes they put a little elbow, and the elbow really didn't show up that well on our slide. But we'll use either of two of these. When we write our not operation, when we say not X, okay, we could either use the apostrophe or the bar. I don't mind which one you use. Okay. How do we define a Boolean function? A Boolean function has at least one Boolean variable, at least one Boolean operator, and at least one input from 0 and 1. It produces an output that's also a member of the set 0 and 1. Okay. Now you know why the binary number system is so handy in digital systems. Well, maybe not, but you will soon, right? Okay, let's look at this Boolean algebra equation. Okay, and how we're making it with a truth table. So truth tables are very important to Boolean algebra. The truth table for the Boolean function x, y, and z, equals x z naught plus y. Okay, and it's shown at the right here. Okay, to make evaluation of our Boolean function easier, we've added some extra columns here. So a lot of times, and actually we saw this in discrete mathematics too. Do you guys remember making these truth tables? Those of you who took discrete mathematics, CPSE 07, okay, it kind of relates to it, right? So what we have here on the left is all combinations of 3 variables. Okay, so 2 to the power of 3 means that there's 8 different combinations that the x, y, and z can hold. When we write our x, y, and z, a lot of times we'll write them with the 0 first, because if we look downward, it is counting in binary. 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2. Do you see how it's 3, 4, 5, 6, and 7? So we have our variables 0 through 8, right? Those are all possible combinations of our x, y, z. When you're writing these 2, you can also see over here a pattern, 0, 1, 0, 1, 0, 1, 0, 1. This one goes 0, 0, 1, 1, 0, 0, 1, 1, and this one has 4 zeros and then 4 ones. And that's usually how we write that. Okay. If you mixed up those columns, it would still be all the combinations, but we usually write them in order like this. Okay. Now in our Boolean equation, we have x, z naught, and then the y. Okay. So what they did is they added a column here for z naught. How do we get z naught? Well, we just flip all the zeros to ones and all the ones to zeros. So do you see how this column is z naught, or not z? Okay. And then the second column here is x times z naught, or it's x and z naught. So x multiplied by z naught and x and z naught kind of mean the same thing. Just remember that your carryover adds back in. Okay. So you just multiply x times z. Okay, that's 0. Notice that when x is 0, they're all going to be 0. It makes sense. And when x is 1, they're all going to equal what z naught equals. You see how when x is 1, then we just have it multiplied times z naught, so we see z naught right here. And then our last column here, we finally take this column, the xz naught, and we OR it, or we add it. Remember that your OR operation is your add operation. We add it to y. So it's 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1. 1 plus 0 is 1, 0 plus 0 is 0. How about this one? 1 plus 1 is 2, but you add in the carryover. Or you can think of it as the AND operation. The OR operation, sorry. 1 or 1, of course, is true. And false or true is true. So you can think of it both ways, and it is good to think of it both ways, that it is the OR operation, but you can also think of it as addition. Okay? And that's the way you can solve a problem like this with a truth table. Meaning that if we built a circuit to represent, okay, this equation here, which we will do eventually, we're going to make circuits to represent this Boolean equation, and we gave it the inputs 0, 0, 0, our output to that circuit would be a false, or would be a 0. If we built this circuit and we gave the input all high, if we pushed all the buttons on, okay, we turned them all on or turned them all high, our output would be a high. Okay? So our first step is just to understand these truth tables, and then we can start applying them to our circuits when we're building them. So that you can always tell what the output to your circuit's going to be if you're given the input. Okay. Now, as with common arithmetic, Boolean operations have rules of precedence. Okay, so order of operations. The not operator has the highest priority, followed by and then by or. And you can think that, hey, that makes sense that you would apply the not operator first. And then the and operator is multiplication, so of course it's going to come before the or operation, which is addition. Okay? So just remember your order of operations. And this is how we chose the shaded function parts in our table, because you do z naught first, you do the multiplication second, and you did the addition last. So these digital computers contain circuits that implement these Boolean functions. So it makes sense that the simpler we can make a Boolean function, the smaller the circuit that will result, the less actual hardware that we have to use to implement this equation or function. Simpler circuits are cheaper, consume less power, run faster, and are easier to build, and are more likely to work because there's less things that could go wrong with them. Okay, so you always try to simplify your Boolean function so that you don't have to implement so much in hardware. Remember, we want to keep the hardware as simple as it can be and add the abstraction through the software. And that way things work. Okay? So with this in mind, we always want to reduce our Boolean functions to their simplest form. This is what makes this chapter fun. We get to reduce Boolean algebra functions. There are a number of Boolean identities that help us to do this. And I don't make you memorize these identities. During the test or wherever, I give you these identities. But it is good to start to remember what they are, because that's how we're going to figure out how to solve some of these Boolean algebra functions. So most Boolean identities have an AND product form as well as an OR sum form. We give our identities using both forms, and our first group is rather intuitive, meaning that it just makes sense. So here's an identity law. If I take a high input, like a 1, and I AND it times x, what will be my output? Whatever x is, because anything ANDed with 1 is just the other value. So if x was a 0 or low, then my output would be low. And if x was a high output, or input, then my output would be high. Do you see? Anything ANDed with 1 or true, anything ANDed with a true value is just going to be the other value. Does that make sense? Or the other input? Okay. All right. We have our null law. That was called our identity law. Our null law says anything ANDed with an input of 0 or false is going to be false. And that makes sense. We're all programmers. We realize that if we have an AND statement, hold on. One second. Just need to readjust really quick. If we have an AND statement and you're ANDing something with a false value, the output's going to be false, because false and something else, it doesn't matter what that thing is. The first one's false, it's going to be false. See how these are really intuitive, right? Okay. And then the idempotent law. Anything ANDed times itself, or ANDed with itself, or multiplied by itself is just itself. You see, true and true is going to be true, and false and false is going to be false. A lot of times you just plug in the true false values in here and you can see, hey, that is true identity. Then we have the inverse law. Any input ANDed with its not self, so this would be true. Let's say x was true, it'd be true and false is going to be false. Let's say x was false. False and true is still going to be false. So we can see that identity, that any input ANDed or multiplied by its not self, or its self reversed, is going to be false. Right? And so if you look at this chart, or you look at this table, after a while you're like, oh yes, that totally makes sense. So that's our AND form of that law. And then the OR form of this law says, in the identity law, when you take 0 and you add it to itself, or its input, so if you take false and OR it, by, let's say, true, so false or true is true. False or false is false. So you can see that, hey, this is a correct law. So anything ORed with 0 is just going to be itself. Anything ORed with 1 is always going to be true, or 1. Okay. If this was 0, your output would still be 1. If this was a 1 or a true value, your output would still be 1 because of the carryover you add in. Same thing here. Anything ORed with itself is just itself. So any input high or low, so high plus high or 1 plus 1 is equal to 1. Or 0 plus 0 would equal 0. False and false. Or false or false would equal false. And then the last one here, any input ORed with its not itself will equal true. And that one always makes perfect sense because if you plug it in, it'd be true or false equals true, or false or true equals true. Okay? So yeah, I don't believe in memorizing these, but they do make perfect intuitive sense, and we'll start to remember them. Okay? All right. Now here's a second group of Boolean identities. Okay, it says it should be familiar to you from your study of algebra. So hopefully it is. So we have the commutative law, the associative law, and the distributive law. Okay, which says x and y is saying the same thing as y and z. So if we switch, them around, it's still the same output. Okay. Same thing over here, x or y is the same thing as saying y or x. We can switch them around, it doesn't matter. The associative law, x and y and z is the same thing as saying x and y and z. And same thing with the OR operation. X or y or z is saying the same thing as x or y or z. So we're just moving the order of operations, but it's still implementing the same logic. Okay, meaning it's still the same output. And you just plug in true and false values for these, and you can see that that's true. And they make sense that it would be true. Okay. And then our distributive law, this one's interesting. This one we use to reduce a lot of Boolean algebraic functions. X or y and z is saying the same thing as saying x or y and x or z. Do you see how you took that multiplication of the y and the z, and then you just ordered them each separately with x and then ANDed the results together? Okay. And then this one over here says x and y or z is saying the same thing as x and y or x and z. And these aren't as intuitive, but if you plug in your true and false values, you can see that you will get the same output for each of these. Okay, that means if you plug in the same input for this side and the same input for this side for x, y, and z, you will get the same output. Your truth tables will look the same. Okay. Our last group of Boolean identities are perhaps the most useful. And if you have studied set theory or formal logic, these laws are also familiar to you. So here's our last laws. These are our last ones. We have the absorption law, the De Morgan's law, and the double complement law. The double complement law makes sense. I think it's pretty easy. X not, that means you're changing x to 1. Let's say x is 1, you change it to 0, then you change it back to 1. You're just nodding it twice, it'll equal itself. De Morgan's law I find very useful. It says x and y, you'll get the same input as if you not both of them and change the and to an or operation. And same thing with the or operation. X or y knotted. So the not operation of x or y is it give you the same output as x not and y not. Okay, so we can go back and forth, and they give us the same output. Now we distributed the not, but we also changed the or operation to an and operation. And it does actually give you the same output. In fact, we can do that one on the board if you want, or on my spreadsheet. We were going to do a couple of these identity laws because they are in your homework as well. We can do that one actually. I always like De Morgan's laws. They're very useful. All right. All right. Cool. All right. In fact, let's do that really quick, actually. Instead of writing it on the board, I'm going to attempt to make it in my spreadsheet here. Let's see, we need X, Y, or Z. All right. And we need 8. All right. So I was going to make a truth table for our X, Y, and Z. Oh well. We'll make these a different color. I was thinking a bigger border, but. So here's our inputs for X, Y, and Z. And what I thought we could do is look at that De Morgan's law and see that it's true and how to write one of these laws into a truth table. So our De Morgan's law said X or Y not equals X not and Y not. Okay. So when we're writing these things, actually we need one more row, don't we? Okay, and then we go 0, 0, so we go 0, 0, 1. So when you're making these truth tables, they're actually pretty easy to make because we're just doing all possible combinations here. And then our last column would go 0, 0, 0, 0. And you can see that we are counting in binary. You can think of it as counting in binary as well. Oops. Oh, I did get an extra row in here. All right. So you can see that 0, 1, 2, 3, 4, 5, 6, 7. Okay, it counts our 8 different possibilities. All right. So we want to do this equation here. So what is X or Y? So we'll start on this side, and we start within the parentheses. Our order of operations says start in the parentheses. And so we just say X or Y. And we can say X or Y, 0 or 0, false or false is false. See how this is making sense? False or false is false. So what is my output going to look like right here? False or true is true. So if even one of the X and Y's are 1, then we're going to get a true output. Do you see? True or true, true or true, true or false, true or false, false or true. So the only time it's really false is when they're both 0 in our OR operation. That makes sense, right? All right. Now we need to not this, meaning that we got to switch all the 0s to 1s and 1s to 0s. And this will be our X or Y not. Okay. So this one's pretty easy. The not operation, like I said, is the easiest. We just flip all the 1s to 0s and all the 0s to 1s. All right. Now let's figure out this one here. It says, or this side of our equation, X naught and Y naught. So first we'll write down X naught. We'll be neat about our things. Now X naught means I just reverse all the 0s to 1s and all the 1s to 0s. So he's going to look like 4 1s and 4 zeros. Same thing with y naught. Y naught. So it'll be switching all the zeros to ones and ones to zeros. Okay. And then we figure out x naught and y naught. So x naught ANDed with y naught, or multiplied by y naught. So what is this column going to look like? You guys tell me. One is x naught and y naught true? Sorry, go ahead. What will it look like? What do you think? Yeah, 2 ones, and then the rest are zeros. And the reason being, they're only true when they're both true, so they're only true in these 2 cases here. Okay. Okay, so now we've just proven De Morgan's law, because we can see that this column is the same as this column for the same inputs. Meaning that if we gave inputs to our circuit and we built our circuit with this equation, it would be equivalent. So if we built a circuit with an input, 2 inputs, and we ORed those inputs together, okay, you can think of it as putting it in parallel, and then we take those inputs and we put them in parallel, and then we NOT their output. So we switch their output from true to false or false to true. And then we take those same inputs and we use an AND gate or put them in series, right? And we take the inputs and we NOT them, and then we put them together with an AND gate. So when we build these 2 equivalent circuits, they will give us the same output for the same input. So we can build our circuit with an OR gate and a NOT gate, or we can build our circuit with 2 NOT gates and an AND gate. And we would get the same output for our input. Which one would be easier, do you think? They're both pretty easy to implement. But one only uses 2 gates and one uses 3 gates. You can kind of think of it that way. Okay? This would use 2 NOT gates and an AND gate. And this one would use an OR gate and then a NOT gate. And I know we haven't gotten to gates yet, but we need to start thinking of how we're going to implement these things, okay, as we're looking at these truth tables and relating it to our hardware. But the important thing is that we saw the outputs are the same, and that's why we have De Morgan's law. We can see that this is always true. Okay? All right, so we have all these identities so that we can reduce our Boolean functions to something easier to implement in our hardware. So here's an example of them reducing a Boolean function using these identities. Okay. So they gave us this input here, and this is our function, x and y, or x naught and z, or y and z. And we want to reduce this function into its smaller form. Okay. So the first law that and sometimes this just kind of takes practice to know which identity. How do you know which identities to use? And actually, sometimes it drives a lot of students crazy because, you know, you're just given this function, and you just have to start trying identities and see if it reduces to a smaller function. Okay. Now, looking at the answer here, it tells us what identities we're using in what order. Okay. So the first one is the identity law. And what was our identity law? It says 1 times x, or 1 and x, is equal to x. So they used the identity law right here, and they said, okay, if I multiply you by true, or 1, so if I AND you with 1, it's saying the same thing as above, so I haven't changed the equation. Okay. Now, why did they do that? So that they could do the next step here as the inverse law. So they did that so that they could introduce x naught into this part of the function. So they know that 1 is equal to x or x naught. So notice that this guy has x inside of him, this guy has x inside of him, and this guy did not, this last part. So they thought, okay, if he has an x variable inside of him, then I can group these guys together. So do you see how they kind of thought of that?
Can we use both and or forms?
Oh yes. You can use all of those identities. Okay, it's kind of like a riddle, really. If you guys like riddles or solving mathematical functions, it's kind of like a riddle. What one could I use to help reduce this? Okay, in practice, so using this kind of trick of multiplying by 1 and then changing that 1 to x or x naught, because remember, x or x naught is true and is 1. By doing that kind of trick like that, I guess it's not really a trick, but knowing that you could apply these two identities to introduce x into this part of the function. Okay? So then they use the distributive law, and they say, this part of our function is equal or equivalent to this part of our function. They distributed the y and z to the x and then the x naught. Okay. And then they take their commutative law right here. So what did they change from this step to this step? All they did was reverse the y and the z to z and y. And that doesn't seem like much of a step, but okay. And then associative twice. So the associative law, meaning they rearrange these parentheses. So they group the x and the y together, and they group the x naught and the z together, and took out the z and then the y. Okay. And then what did they do? They just rearranged these. Do you see how x naught z is over here and x y z is over here? They just rearranged those two. Because when you OR something, it doesn't matter which order you're ORing, right? And that's the commutative law. Okay. And the reason they did that is so that they could pull the xy out of these two parts of our function. So they pull the xy out of those two parts of our function, and they pull the x naught z out of these two parts of our function. And now they're left with 1 or z or 1 or y. And what is 1 or z? True or something is true. Okay? So then they get rid of that z variable. And then over on this side, they say 1 or y, so it's true or something. Right? It's just true. And now they reduce a function with the null property, our law, to xy, or x and y, or x naught and z. So how did they get from here to here? Well, they had to do all of these steps, right? But when you're starting up here, sometimes it's hard to see that you can get to here. Okay. So when you're starting up here, what I look for is say, hey, what could I pull out of any of these that could reduce this function? Okay. And they recognize that if they put the x in there, they could make an xy and an xz and be able to group them together with these two and then reduce it. Do you see how kind of you can say, oh yeah, if I added an x to this y and an x to that z, I could group these two guys together with him and then reduce it. And at first it is hard to see, and I've taught this a couple years now, and a lot of really smart students sometimes have trouble with these. But the more you practice them, the easier it gets. And there's really not that many identities you can use. And if you try one way and then it starts getting into a bigger function and not a smaller function, then hey, maybe I should start over and try something else at first. Try a different kind of logic. But a lot of times you just try to group them to get rid of one of the inputs out of part of the function. So what this means is if I wrote the truth table for this function and I wrote the truth table for this function, they would have the same output. That's what that's telling you. When you reduce these Boolean algebra functions, you're going to get the same output for the same input. Actually, for any of these. If I implemented any of these parts, I would get the same output for the same input because they're all the same equation. I know that sounds weird, but it's true, okay? So they are all the same equation. They're just in different forms. Just like when we learned Boolean numbers, it was always the same number, just in a different form. These are all the same equation or function, just in a different form. Okay, they're all equivalent. Which one's easier to build in hardware? This one uses 3 AND gates, a NOT gate, and 2 OR gates. This one uses 1 OR gate, 2 AND gates, and a NOT gate. So this one is easier to implement in hardware than this one. You see how reducing these makes our hardware easier. And that's the purpose of doing Boolean algebra and reducing these. Okay. It says sometimes it's more economical to build a circuit using the complement of a function and complementing its result than it is to implement the function directly. Okay. De Morgan's law provides an easy way of finding the complement of a Boolean function. So remember that x and y knotted is the same thing as x naught or y naught, and x or y naught with the not operator applied is saying the same thing as x naught and y naught. Okay. So remember, you just flip the sign, or you can say and to or to and then distribute your not operator. It says De Morgan's law can be extended to any number of variables. Okay, and this helps us reduce our functions, knowing this. Replace each variable by its complement and change all the ands to ors and all the ors to and. Okay, pretty easy actually. So let's say that we have this function here and we not the entire function, meaning we reverse the entire function. Okay, so they put the not operator on the outside of the entire function. So notice that our and operators will now turn into, our or operator will turn into an and operator, do you see? And we take all these as, we think of x, y as one input, and we not the whole thing. Do you see how we have to not the whole variable? Same thing with this guy, we'll not the whole variable, and we not the whole variable. And then you can distribute your not operator. Same thing with De Morgan's law. So x and y knotted is the same thing as saying x naught or y naught, and x or y naught, and x naught or z. See how that's the same? Hopefully you guys can see that those are just using the De Morgan's law over and over again. Okay. Now why would this be easier to implement than this? Actually, this one be easier to implement than this one. Maybe in this case it's not so much, but in other equations we can actually reduce our hardware. Or it'll help in reducing the entire equation. All right. So through our exercises in simplifying our Boolean expressions, we see that there are numerous ways of stating the same Boolean expression. These synonymous forms are logically equivalent. So just like I was saying, all those functions, if you give them the same input, you'll get the same output. So they're logically equivalent. Logically equivalent expressions have identical truth tables. Same input, same output. So in order to eliminate as much confusion as possible, designers express Boolean functions in standardized or canonical form. There are two canonical forms for Boolean expressions, sum of products and product of sums. Recall the Boolean product is the AND operation and the Boolean sum is our OR operation. So in the sum of products form, ANDed variables are ORed together. So this is our sum of products. So this is a product, and we're taking the sum of them. Okay. And this is our product of sums form. Okay, so a lot of times we try to get our function to look like this in a sum of products form or a product of sums form. because that's a standard way of writing a function. Okay, so a lot of times we try to get it into this form. It's easy to convert a function to sum of products form using its truth table. We are interested in the values of the variables that make the function true. Using the truth table, we list the values of the variables that result in the true function, and each group of variables is then ORed together. All right. So what they did is they took this truth table like we did before, and this is our output. Notice that they skipped all the other columns because they did from up above. I think this is the same equation that they used in up here. Do you see how they showed you how they did it up here? So we have 0, 0, 1, 1, 1, 0, 1, 1. But in this slide, they just show you that last column. Okay, but it is the same column. Do they show us? Oh yeah, so they show us. So in sum of products form, they take all the one inputs. So this is our true input, our true output, sorry, output. One of our true outputs is x naught, y, z naught. Here it is, x naught, y, z naught. Or x naught, y, z. X naught, y, z. Or, here's our other true output, x, y naught, z naught. Or x naught, y naught, z. X, y, z naught. Or x, y, z. Do you see how you take all the true outputs, and that'll be our output here. So, does that make sense how we translated all the true outputs, or all the ones in our truth table, and we look at the values that made that true. So this would be true or true or true or true or true. And that will be the output to our function. Does everyone see how we got that sum of products form? Now, what if we wanted to reduce this to its product of sums form? We would just apply the De Morgan's law and make it a product of sums form. Okay. All right. Actually, this is a good place to stop. We're going to stop at 3.2. So I thought we could practice a couple problems together so it's fresh in our head. We don't have to do a tremendous amount. We'll do some today and some on Thursday. Okay. But I was going to practice some problems that were not homework problems, but were similar. Okay. So number 3, we have a function with x, y, and z. So we do actually write it like this. So these are our inputs, right? And then our output is x, y naught. Our function is x, y naught, and x or z. Okay, now you guys have your De Morgan, or you have the slides up so you can look at those identities. Even bring up your identities. We can cheat and look at our identities. Now we want to reduce this function. So that means get rid of maybe a variable, or, get rid of some of the logic and make it simpler to implement in hardware. Okay. So which law do you think we should apply? And I'm cheating right now. I'm looking at which one they applied. So there's different ways that you could go about it, but it is hard at first. But which one do you want to apply, maybe? Well, we have this AND operator. Yeah, we could do distributive law at first. Okay. Now that's probably what I would have thought of is a distributive law. Now they applied De Morgan's law, but let's just try the distributive law, because that was the first thing that came in my head, and I heard somebody, I think it was Mark, right? You said distributive law? Was it? Oh. I thought somebody said distributive law. Okay. But when I looked at that, I thought, okay, well, what if I distributed?
Well, if you do, you get rid of the one x.
Yeah. So if I distributed and did my distributive law, and we know how distributive law works, we can remind ourselves, make sure I'm doing it right. But with distributive law, with the multiplication, you can see for the OR form, you would just take the x, y naught, or with x, y naught, z. There's our distributive law in that second column there, okay, in our slides. Okay, so that form, we distributed the outer or the ANDed variable to our variables. Okay. Now, can we do anything else out of there? What would we do next? What is x and x? X. So which one was that? If we get rid of this x, which law was that? It is... I forget the names of the laws too, to tell you the truth.
Indefinite.
Which one is it?
Indefinite.
Oh, idempotent, yes. Idempotent. I think it's pronounced idempotent. Okay. So what if we did get rid of, so x and x is just x, and then we still have our OR. Okay, what could we do here? What if we took out the x, y naught? Yeah, associative law. What if we said x, y naught is saying the same thing as 1 or z? Is that our associative law? Which one is that? Now that's not one associative law. That is our distributive law, right? Yeah, that's our distributive law. I gotta memorize things like that. I hate memorizing things. During your test and everything, I give you guys the cheat sheet of all the laws too. Okay. And then, yeah, so this is the null law. True or something is always going to be true, so we can get rid of that. And actually, we made it smaller than what they did in the text. And I'll show you what they did in the textbook answers. Okay, but I believe we did that correctly. Actually, I have to stand over here so I can see it on the camera. But we've reduced this function that was using an AND gate, a NOT gate, another AND gate, an OR gate, to just using one AND gate and one NOT gate, and it doesn't even matter what Z is. Okay? And so when we do our digital electronics next week, what we'll do is we'll build this circuit and then this circuit, and you can see that the same inputs for this circuit will give you the same, same input here will give you the same outputs. But which one's easier to build? That one, of course. Okay? So, and if you drew your truth table, you would also see that this column is the same output as this column. And so that's a way you can double check yourself that you've done these right, actually, is to make a truth table out of it, and then check that this column has the same ones and zeros as this column, the same output. Okay, and we can double check ourselves. Okay? In fact, I'm going to write it over here and we'll double check ourselves. But I'm going to do the truth table on Excel because I hate trying to draw two truth tables on this board, actually. Okay. Now I'll show you the way that the textbook did it, just to see another way, because these are the harder ones, right? And so what they did is they applied De Morgan's law. Oh, because that's what the problem said. But it's okay, we practiced it. It says using De Morgan's law. But that's okay, we still figured out how to, and that was the hard part anyways, reducing these functions. But they said apply De Morgan's law. So let's just practice applying De Morgan's law like they said in question 3. And it says write an expression for the complement of the function. Okay. So let's apply De Morgan's law. So they want the complement of the function, meaning that they want us to complement the function. So what is the not operator for this function? Okay. So what I do is I take the entire function and complement it. Okay. So when I apply De Morgan's law, what do? You take all of your variables and knot them. Okay. So I treat this as a variable and then I knot it. I change all my multiplication to addition. And then I take this variable and put the not operator on it. Do you see how I distributed the not operator? Knotted and knotted. Remember that this y is still not, and then x and y naught is knotted. Okay, and then x plus z, we apply the not operator. Okay. So then we have to distribute that not operator. So what is De Morgan's law again? We'll apply De Morgan's law again. This will be x naught, or we change the multiplication to addition. And this was x, so now he's x naught. This one was y naught, and y naught naught is y. And then the same thing here. We'll apply De Morgan's law to this. So this one will be x naught and z naught. And so this is the complement of the original function. Oh yeah, so it was right. They just put extra parentheses in there. I was like, wait a second, we did that right. But they just put some extra parentheses in there. Okay? Actually, if I don't stand correctly, we can't see the board. All right. So that was number 3, just so you know. Okay? And we did it 2 ways. Let's try number 5, which is another one for reduction. It's actually using De Morgan's law again. Actually, that one might be really hard. Actually, we'll skip that one. I'll come back to that one. Because in the answer key here, all they're doing is applying De Morgan's law, and if we really want to reduce it, we'll come back to that one at the end if we have time here. But let's try number... Now, I gave you number 10 as your homework problem. And is there an equivalent one to number 10? Oh, maybe I could just make one up. There really isn't an equivalent one to number 10. But number 10 says, show that, and I'll write it down so we know what number 10 is. Show that x is equivalent to x and y, or x, y naught. And it says, show this with a truth table or using Boolean identities. Okay, so you had to do it 2 ways. Okay. Actually, this one's pretty easy. Yeah, yes, you're very good. Yes, you would use your distributive and then your inverse law. I guess we could still solve this one, right? So what would you do? Yeah, distributive. And then true or false is, or false or true is always true. And so then he just equals that guy. And that was our, distributed, inverse, and then identity law. Okay? Distributive, inverse, and then identity law. So and then it says, okay, that was how we showed it with Boolean identities. How would you show this is true with a truth table? Okay, I said I wasn't going to make truth tables, but this one's pretty easy. It only has 2 inputs. So 0, 1, 0, 1. Remember, if you only have 2 inputs, all possible combinations would be 2 to the 2nd power. You only have 4 possible combinations. It's always 2 to the power of your inputs. So if you have 3 inputs, you have 8 different ways you can combine them. If you have 2 inputs, there's only 4 different ways you can combine them. And if you have 1 input, there's only 2 ways you can combine them, either 0 or 1. So you just, it's always 2 to the power of how many variables you have. Is how many different combinations of inputs you can have. So with a 2-input truth table, you only need 4 rows. Remember that. Actually, I do remember that last time around, people would still make 8 rows, but no, you only need 4. Okay? All right. So if we were to show this law with a truth table, you would just make the x and y. And we know x and y, that's pretty easy. And then x and y naught. What does that look like? X and y naught. Okay. So you can multiply them if you want. Now I just did it really fast. Now you could make a y naught column if you wanted to. Okay. And on theirs, actually they skipped the y naught column too. But remember, your y naught is just going to be the opposite of your y. Okay. So x and y naught. And notice how I figured that out. X and y naught. This was y naught. Okay. Would be 1 here. And would we have 0 everywhere else? Yes. This is the only case that it would be true, is when it's x and y naught. Right? Yeah. Just making sure. And then the last column would be our final column here. It'd be x and y, or x and y naught. And you just or these two columns together, and when is it true? Yeah, when either one of them is true, so we'll have 0, 0, 1, 1. You see? So how did this prove it? Well, we still have to write it. So here's our true outputs. What's our true outputs? X is 1, y is 0, x is 1, y is 1. So we can write it in product of sum or sum of products form. Okay, so if we wanted to write it in product of sums form, it would be, what would it be? Sum of products. It would be 1, it would be this. This is our sum of products form, actually. It would be x and y naught would be our first product, or x naught and y naught. I mean, sorry, x and y. Not, because they're both true, so it'd be x and y. There's our sum of products form. How do we write our product of sums form? You could do De Morgan's law to make it into the product of sums. Okay. So when we do De Morgan's law, we can see it's x naught or y. Or maybe I need to write it out, actually. And then we do our distributive law. X naught or y naught. And there's our product of sums. So this is equivalent, this sum of products is the same as our product of sums. Meaning, not the same, but you know what I mean. They're equivalent to each other. All right? Actually, we did number 10 together, so you better not get that one wrong, right? All right. Now I gave you number 16. This one says simplify the following functional expression using Boolean algebra and its identities. This is that simplification one. And actually it has 3 equations in it. So let's do number 14 together. Let's simplify a few of these. Okay. Because I think this is where we kind of need to focus, is simplification. Because that's where students had the hardest time, is trying to simplify these things. All right. So in number 14, it says simplify the following functional expressions using Boolean algebra and its identities. List the identity used at each step. So it's like how we did that first problem. We reduced it. Okay. So we have y and x naught or x or y not. Okay, so we have it looking like that. making sure I wrote it down wrong so we know. Okay, I'm not even going to look at it. Now, what would you think to do first? This is always hard. Distributive. Who said distributive? Good. Whenever you see like a letter on the outside, you always say, well, let's try to distribute it and see if I can group some of these into new groups to get rid of something. So a lot of times if you're anding toward a variable like this, try distributing it to see if we can regroup them, to get rid of something. We want to get rid of something, right? So we can use our distributive law. So we distribute it to our x naught, and then we distribute it to our x plus y naught. Okay, so we distributed that. And in your homework, they want you to write down the laws. So you're supposed to write them down after you use them. Okay, so for your homework, that's how they want it. Okay, so then it's telling you which law you've used. Okay, what should I do now, do you think? Yeah, you could do either De Morgan's law, okay, or distributive law again. Okay, I would probably do distributive law again. Actually, in the answer, they did do De Morgan's law. Okay, but if you did distributive law, you'd probably get the same. Well, you would get the same thing, right? So we could try it both ways. Let's try distributive law first. So if I did distributive law, oh, actually, I can't do distributive law yet. Yeah, I have that not operator. So yes, it made very good sense that we used De Morgan's law. Because I can't distribute in here with that not operator. Remember, order of operations, not comes first. So we need to take care of that first. Okay? So, using De Morgan's law, this would be x naught. The or turns to an and we flip the variables, either x or x naught, y or y naught. So that's, what is that? De Morgan's law. Okay. Now we can use our distributive law. Okay. Or actually, it's not called a distributive law. What is it called?
Associated?
I guess it would be distributive and, yeah, we're going to flip them around. So I'm going to put x naught in front here. Remember when we flipped these two? So I'm going to distribute him first, and then I'm going to switch the x and the y, which remember is the same thing. What is that, commutative, I think?
Yeah.
Yeah. Okay. So that was distributive, and actually I did 2 steps in one, and you can do 2 steps in one if you want. I don't mind. Okay.
Associated then commutative.
Yeah, commutative. Okay. Hey, we're getting somewhere. Okay, what should we do now? Do you see something in here? If we have y and x naught, we'll leave him alone. What if we grouped these two together? I bet that's a law. Because true and false, or false and true, will always give you false. Remember, you could always plug in the true-false values, and it makes sense, you know, how these laws work. Okay, which law is that? So this guy will be reduced to 0 or false. Okay. And which law was that one? Oh, the inverse law. Okay. And then what are we going to do here? What is something anded with a false? It's always false. True and false is false, and false and false is false. So which law was that one?
No.
Yeah, the null law. So we can just get rid of that guy because, hey, he's going to be false anyway, or 0. Okay, you can always think, hey, I'm multiplying by 0 at 0 too. Because remember, multiplication and addition and or work the same way. Okay. And so then we're reduced to yx naught. Yes, much easier to implement. One AND gate and one NOT gate. And we don't even care what the third input is. Well, actually, we didn't care anyway. He wasn't part of our input. We only had 2 inputs. Okay. Now, if we wanted to check this thing, that it equaled the same as this, we could make a truth table. Okay. So I'm going to put that, I'm going to make a truth table out of this guy. So this is number 14A. But you can definitely see that this is the same as this. When you make that truth table, they'll have the same columns. Okay. In fact, I think in your exam I did have a big problem where you reduce it and then you make a truth table to check these. And everyone realizes how to make a truth table to check these? You just make a truth table and then you'd put, this equation, you'd break it down into its columns and then figure out what your output is for this function. You figure out what your output for this function, and the 2 columns should have the same output, the same 1s and 0s. I don't want to do it up here. I would do that one on Excel if you want. We can do that one on Excel. Okay. But that's how you would reduce that function. Let's practice 2 more, and then we can change gears here. Okay. So let's practice just a couple more of these. It's good for our brains, and this is what Boolean algebra is, really. And after you start getting the hang of it, it is really easy, especially compared to some of your calculus problems I've seen. This is actually pretty easy. Okay? So, yeah. Let's do the second one here. It's x naught, y, and z, or xz. All right. Now, looking at this guy, I won't even look at my answer. What do you think we should do? Looking at him, you can see that this one has an x, y, and z, and this one does not have the y inside of him. Maybe we could use that trick to put the y inside of him. Do you guys remember how to put the y inside of him? Actually, they do that in there. Okay. So you can kind of remember that trick. So remember that if we multiply this function times 1, okay, it's not going to change it at all, and that is called our identity law. Okay. This is kind of like the example that we had on the slides. So then we have x naught, y, and z. And now we can take that 1, and it's the same thing as saying y or y naught. Because y or y naught is 1. So we can change that 1 into y or y naught. And that is called our inverse law. Now we can use our distributive law. Okay, so we have x naught, y, or z plus x, y, z, or x, y naught, z. Now I applied actually 2 laws here. I distributed and I rearranged the variables, and that was called our, which law was that one? Yeah, commutative. Okay, so it was both of them, inverse and commutative, right? Okay, now what should we do? What do you think? Wait, did I do that right? Hold on. Oh yeah, that's right. All right.
Factor out an x, and then factor out a c, and then you have y plus y naught, and it would be is equal to 1.
Wait. So what did you say?
I went back. Fair enough.
Which one? No, it might have been a good idea. What did you say?
I just undid it.
Okay. Oh, undid it, yeah, and put it back the way it was. That does come to mind, right? Now, they did something a little bit different. And the reason that they did this, okay, is they thought, well, what if I could group these two get together, so this equation and this equation, and I could pull out the x and x naught. And then what if I could group these two together, and I could pull out the y and y naught. Okay? But I need two of these but two of these. And so what they did is they said, okay, and then they ORed it by itself again. They repeated it. And is that the same thing? And that is using the law of, they call it the idempotent law. And what they did, see how it's the reverse of the idempotent law? Because x or x is just x. So they're saying x, y, or z is saying the same thing as x, y, or z or x, y, or z. Okay, so that they could have two of these, so they could group these two together and those two together. So I guess that would be another trick. Okay, and they called it the idempotent law. Okay. So then we have x naught y or z, and we can group it together with the x, y, and z. Or x, y, and z, and x, y naught z. And that was our associative law. This is associative. Okay. Now we can do something here. Okay. Okay. So what they did is they took the x and the x naught. Oops. So x naught and x. And which law is that? That was our reverse of our distributive law, right? So they did our distributive law, and they saw, okay, I can pull out the y, z out of both of these and then have x naught or x. And then same thing over here. I could pull out the z and z naught. Because I see that they're both, wait. Sorry, that one was y or y naught too, right? Not z or z naught. It's z and z, but it's y or y naught. So they pull out the y and y naught, and then see that both of these are distributed or multiplied times xz. Okay, and that would be our distributive law. Distributive law. Now what can we do? Yeah, the inverse law. Okay, we see that x naught or x, or false or true, is always true, or 1. Okay. And then same thing over here, y or y naught is true, or always 1. That's our inverse. And then we finally get reduced to yz plus xz. So y and z or x and z, and that's our identity. And it is in sum of products form, okay, which is a standard form. Do you see how this is a sum of products form? It's sum of our products. If I wanted to write it in product of sums form, I could do the De Morgan's law and write it in product of sums form. But a lot of these answers, and in a lot of books, they always write it in the sum of products form. A lot of times. But notice that the product of sums form would be equivalent. So this equation, our function, was then reduced to this function. Okay? And that would be okay. Okay, let's try one more. Everyone kind of got that one? And it is recorded. You might have to zoom in, huh? Yeah, the kind of odd things that we did, just to kind of review, like the tricks. was putting that 1 here and changing it to y or y naught, so to put the y into this part of our function. And then the other odd thing we did was that we doubled this. We made this into 2 of him with the idempotent law so that we could group these 2 together and these 2 together. Those 2 products and those 2 products together. Okay, so just kind of remember things like that, and it'll help us reduce some other ones. Okay, let's do the last one, and the last one is actually the long one. That one was short. All right. But this one might be a little bit easier. It's a longer equation, but if you start out with a longer equation, sometimes it's actually easier to reduce it because you can apply more laws at first. Okay? And this will be 14c. And our function looks like this. It says x naught or y or z naught naught or x y naught z naught or yz or xyz. All right. So looking at this guy, what do you think you would do first? Hopefully many of you thought, okay, I need to get this not operator out of the way. Okay? Get it out of the way, use De Morgan's law, distribute that not operator, and then you could have a sum of products form, then we can start regrouping things. So hopefully you kind of thought of that. Okay? So when you have an equation like this and it has a not operator on part of it and not on the rest, just distribute that not operator with De Morgan's law. Okay? So we'll apply De Morgan's law. I'm just going to put dm now for De Morgan's law. It's hard for me to reach over there. Okay. So applying De Morgan's law, what do? This would be x naught naught, which is just x. All of our OR operators become AND operators. So it's going to be y naught. And, so our OR operator becomes an AND operator, and we not naught. So z naught naught is z. Okay, so using De Morgan's law, we see that this is equivalent to this. Okay. And then we have the rest of our function. All right. So what would we do next? Yeah. Do you guys see the associative? Okay. Right here, right? So right away, not even looking at our answers, I can see that this one is xy naught. This guy has xy naught. So I can take that xy naught and pull it out of. Actually, that was distributive, huh? Were you thinking of something else, Yesenia? I thought of distributive right away because I saw that these guys had the same xy naught. Why not pull that z naught? Now, there's different ways that you can reduce this, so this is just one way. Okay. So if I use distributive law, I could do this. Now, what were you thinking, Yesenia? Associative. How would you use associative?
Well, I don't know. I don't know.
Okay. But there are other ways. You can start applying different laws and see how it is. But when I saw that these had the same, you can always pull out that part and then use your distributive law to pull that out. Because when I have z or z naught, what is that?
1.
Yeah, that's our 1. And which law is that one? Yeah, our inverse law. Okay. All right, so now this is reduced to x or y naught, or x and y naught, sorry. Now looking at this side, what could I pull out of both of those? I could pull out the y and z. Notice that both of these have y and z. So I could pull out the y and z, and I would have 1 plus x. And that was our distributive law again, right? Hey, we're getting somewhere. What is 1 or x? True or something else? It's always true. Which law is that one? I forget. Null law, yes. Yeah, you're pretty good, Manuel. All right. Can we pull out anything else? I think that's pretty reduced. Notice that this would be immensely easier to implement in hardware than this one. So by reducing this Boolean equation, now I can implement in hardware the same thing. And for the same inputs, I'm going to get the same outputs. So it doesn't matter how I implement this thing in hardware as long as I'm getting the same outputs for the same inputs, right? So this would be a much easier way to implement my hardware than up here. This uses how many gates? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 gates. And this one only uses 1 AND gate, 1 NOT gate, so 2, 3, 4 gates. So it's immensely easier to implement in our hardware. And that's the purpose of reducing these Boolean algebra equations. Okay, so that we can do our hardware in the simplest form and it'll work. Okay. So, you know, the slide presentation from your textbook, it said, hey, we start with our high-level thoughts. We reduce them down to our Boolean algebra equations. So our high-level thoughts, we make it into a truth table. We take that truth table, make it into a function. We take that function, reduce it, and now we can implement it in hardware. And this is how we're getting our high-level logical thinking to work inside of a computer through the hardware. Okay? And it is an abstract idea, and you could see back in the day why people had a really hard time visualizing this and why this would be hard for them to visualize that a computer could do this. Okay? So, but it does work, obviously. That's how we got Facebook and Twitter and Snapchat. My daughter loves it when I Snapchat her. I figured out Snapchat. She's like, oh my God. She's a senior in high school, yeah, so she loves it. All right. So we'll do some more problems on Thursday. In fact, you can look at your homework problems or look at